This is one of several modules in which we will look at logistic regression models in more details. Arguably, after linear regression, logistic regression is one of the most common regression techniques. As you know by now, logistic regression arises in the context of a binary outcome. The motivation for the logistic regression can come from econometric data in terms of the binary choice model, or it can also come from mathematical considerations due to the fact that the logic link is the canonical link in the situation where we have a binomial family. We shall look at more detail at the fitting, inference, interpretation of coefficients, and goodness of fit for logistic data in this module. The learning objectives for this module. We are going to look at more detail in logistic regression. First, we will look at the problem of checking assumptions, and we shall see that it is not as easy to check assumptions for binary data as it was for continuous outcomes. We shall look at more detail at the problem of making inferences, and finally, we shall look at the deviance, which is the standard measure of goodness of fit. Logistic regression is a popular technique in many fields, including biostatistics, econometrics, etc. An intuitive reason for its popularity can be motivated as the binary choice model, which we have seen in another module. There is also good mathematical justification for using this model, and the reason is that the logic link turns out to be the canonical link for the binomial family of distributions. This means that the likelihood, the score equations, the information matrix all simplify, as well as the behavior of the estimates in terms of their asymptotic distributions often require smaller samples. Hence, based purely on mathematical considerations, the logistic regression model is also popular and is often the regression model which is used as the default in many software programs. Parameter interpretation is also an important reason why the logistic regression model is very popular. Now let us assume, to begin with, that we have a single covariate x, which is also binary, and a single outcome y, which is binary, with pi x equal to the probability of y equal to 1 given x equal to small x. The logistic regression model is then given by pi x equal to exponential of alpha plus beta x by 1 plus exponential alpha plus beta x, where alpha and beta are unknown parameters to be estimated from the data, or in its more common form, logit of pi x equal to log of pi x over 1 minus pi x equal to alpha plus beta x. So thus, the logic link is used because here we have equated the logic link function to the linear predictor. Now, if we write out these two equations setting x equal to 0 and x equal to 1, it is possible to see that e to the power alpha emerges as the odds of the event y equal to 1 among the group x equal to 0. This is often termed as the baseline group. E to the power beta turns out to be the odds ratios comparing those with x equal to 1 to those with x equal to 0 in terms of the odds of the event y equal to 1. In the case where x is not discrete but continuous, we can similarly write out the two equations for x equal to some given value x naught and for x equal to x naught plus 1, in which case it is possible to see that e to the power alpha is now the baseline odds of the event y equal to 1 among the group x equal to 0, whereas e to the power beta is the odds ratio for a unit increment in x. That is, if we look at any two individuals who are 1 unit apart in x and compare the odds of the event y equal to 1, we would expect that ratio to be equal to beta. Now, of course, you know that there are many alternative choices of link for the binomial distribution, and although the logic link has a good property in terms of being canonical, very often it is not possible or acceptable in terms of an intuitive perspective. So the binary choice model, for example, may indicate that the probit distribution is more applicable. It is of course possible to use other choices for the link function, for example the complementary log-log link or even the log link. So one way to compare the appropriateness of choice of link is of course to fit all possible models and to compare a goodness of fit criterion or the value of the likelihood from these models. An alternative is to try to derive some graphical techniques for checking the appropriateness of the link. Now, when we set out to do this for binary data, we notice at once that such assumptions are difficult to check. This is because the binary data is scattered as zeros and ones, and so when we try to draw the analog of a scatter plot, we will just see two clusters of points, one at 0 and one as 1, which make it very difficult to determine the position of a line passing through them. Now, it has been proposed that an ad hoc adjustment of adding a constant c to y be used so as not to get values of log 0 or minus infinity in the plot, and empirically it has been observed that the adjustment log of yi plus half over ni minus yi plus half, symbols having their usual notation, turns out to be closest to the true logic. Now, of course, when x is continuous and all ni is equal to 1 or all ni are small, this is not very satisfactory. In such a situation, it might be a better idea to bin the covariate x and to find the ratios and run a smoother on these proportions. Now, two examples of checking the appropriateness of the length. This comes from the O-rings data, and as you can see, the plot of the empirical proportions of damage corresponding to various temperatures does not really reflect the true underlying nature of the curve. Another data which we shall consider for this paper is the horseshoe crab data, which has been well studied by Agresti, and when we look at a similar smooth curve from the horseshoe crab data, we see that it gives a rather good indication that the logistic regression will fit well. Now, thus far we have been considering only prospective studies. So, a prospective study essentially denotes that we have been assuming the explanatory variable x to be fixed and the response variable y to be random, and assume that sampling is from the distribution of y given x. However, an important class of sampling designs is the retrospective sampling design. You may, for example, have heard about the case control design in biomedical studies. In such situations, for samples of subjects having y equal to 1, who are called cases, and y equal to 0, who are called controls, the value of x is observed. Now, we will say that there is an association if the distribution of x differs between the cases and the controls. In retrospective studies, we can estimate odds ratios and proceed as usual. Now, let us suppose that Z is an indicator whether a subject is sampled. So, Z equal to 1 indicates that the subject has been sampled, and no is indicated by 0. Let P1 equal to the probability of Z equal to 1 given y equal to 1. That is, P1 is the probability of sampling a case, and P0 equal to probability Z equal to 1 given y equal to 0 is the probability of sampling a control. So, even though the conditional distribution of y given x equal to small x is not sampled, we need a model for probability y equal to 1 given z equal to 1 and x, assuming that probability y equal to 1 given x follows the logistic model. By an application of Bayes' theorem, we get the first equation on this slide. Now, suppose that probability z equal to 1 given y and x is equal to the probability of z equal to 1 given y for y equal to 0 and 1. That is, once we know that whether a subject is a case or a control, the covariates do not give any extra information for the probability of sampling inclusion. The sampling probabilities do not depend on Z. Under this assumption, substituting P1 and P0, we get probability of y equal to 1 given z equal to 1, x equal to P1 into exponential alpha plus beta x by P0 plus P1 exponential alpha plus beta x. Reparametrizing this can be seen to be of the form logit probability y equal to 1 given z equal to 1 and x equal to alpha star plus beta x. Alpha star is some function of alpha and the sampling probabilities, that is, alpha star is equal to alpha plus log of P1 by P0. Beta is, of course, the same beta as we have used before. So, the implication of this is that the odds ratio is invariant to study design, and if we were to fit a logistic regression to a case control design, ignoring the case control nature of the data, the estimated intercept will no longer have the same interpretation, but the estimated log odds ratios can be used as before. Of course, after estimating the coefficients of the logistic regression model, we are next interested in performing inference. Now, note that since we have a likelihood and that we use maximum likelihood inference, we have available 3 ready-made estimation or inference procedures. The first is the Walls test, the second is the likelihood ratio test, and the third is the score test. We can get confidence intervals by inverting any of these tests, and we can use another likelihood measure of goodness of fit called the deviance to see or compare alternative model formulations. We next come to the problem of checking goodness of fit. Now the deviance compares the saturated log likelihood to the fitted log likelihood, and the expression for the deviance is as given on this slide. A problem, however, arises for the case where we have ungrouped data. Ungrouped data refers to the situation where Ni is equal to 1 for every I. In this case, it can be shown that the deviance becomes a function of the true betas, that is the true log odds ratios, and this is not a desirable property. This undesirable property of the deviance is referred to in the literature as the sparseness problem for ungrouped data. An alternative measure of goodness of fit has been proposed by Hosmer and Lemshaw. Hosmer and Lemshaw proposed a Pearson statistic which compares the observed and the fitted counts for a partition. Let Yij denote the binary outcome for observation j in group I of a partition of the data based on covariate values, I equal to 1 to g, say, and j equal to 1 to nj. Let Πij hat denote the corresponding fitted probabilities for the group fitted to the ungrouped data. The Hosmer and Lemshaw statistic then equals summation j equal to 1 to g, summation over j Yij minus summation Πij hat whole squared by summation Πij over j into 1 minus summation Πij hat over Ni. Now, while many observations can have the same estimated probability, there is some arbitrariness in forming these groups, as a result of which different software can report different values of the Hosmer and Lemshaw statistic. For more details on how to form the partitions, you are referred to the publication by Hosmer and Lemshaw in 1980. An important class of regression models are those which give rise to ANOVAs. So these, as you know, are regression models with categorical predictors, or more commonly known as factors. We can have the equivalent of this for logistic regression. So suppose we have a single factor x with, say, capital I categories. We then have an I cross 2 table, and in row I, yi is the number of outcomes in the first column out of ni trials. Yi is binomial with parameter pi I, and the logit model with a factor can be written as log of pi I over 1 minus pi I equal to alpha plus beta I. So this resembles the ANOVA model. Now, of course, as for the standard ANOVA model, we can have many reparameterizations of this. For example, we could also reparameterize as logit of pi equal to alpha tilde plus beta tilde, where alpha is alpha tilde minus beta I, and beta I is beta I tilde plus beta I. Note that when we have capital I categories, we can introduce I minus 1 dummy variables and also get the dummy variable formulation of the model as logit of pi I equal to alpha plus beta 1 x1 up to beta I minus 1 xi minus 1, where x1 to xi minus 1 are the dummy variables for any I-1 of the categories. Now, in the case where we have ordered factor categories, we can use more parsimonious model formulations. So, for example, if the scores x1 to xi describe distances between categories of x, we can fit the linear logit model, logit of pi I equal to alpha plus beta xi, in the situation where we expect that x has a monotonic effect on y. So, independence between x and y in this special case is denoted by beta equal to 0. Armitage and Cochrane were among the first to emphasize the importance of using ordered categories in a contingency table. For I/2 tables where the rows are ordered and capital I independent binomial ni pi I variates yi, they propose a trend statistic for testing independence. This is done by partitioning the Pearson statistic for the hypothesis. So, specifically they use a linear probability model pi I equal to alpha plus beta xi. The prediction equation is pi I hat equal to p plus b into xi minus x bar, where b denotes the usual regression coefficient. The Pearson statistic for testing independence is then x square I given by x square I equal to 1 over p into 1 minus p summation of I ni pi minus p bar square, which is of the form z square plus x square L. Well, x square L is equal to 1 over p into 1 minus p summation ni pi minus pi I hat square. When the linear probability model holds, x square L is asymptotically chi-square with degrees of freedom I minus 2. The statistic z square with df equal to 1 can be used to test the hypothesis h naught beta equal to 0, that is, the test for the linear trend in the proportion. This test of independence using this statistic is called the Cochrane-Armitage trend test. We can of course generalize very easily to the situation where we have multiple logistic regression, that is, we have p covariates x1, x2, xp. The logistic regression equation can easily be generalized to logit of pi x equal to alpha plus beta 1 x1 plus beta 2 x2 and so on up to beta p xp, where x now denotes a vector, a p-variate vector with components x1 to xp. The score equations here are no more complicated. Their log likelihood is given on the first line of this slide, and because this is the canonical link, the likelihood equations will simplify and in fact are given by summation over I yi xij minus summation over I ni pi I hat xij equal to 0 for j equal to 1 to p. The information matrix too will simplify, and note that the information matrix will not be a function of y because we have used the canonical link. In fact, minus del square L beta del beta prime is given by summation of xia xib ni into pi I 1 minus pi I. This means that the observed information and the expected information will be the same, and Newton-Raphson and Fisher scoring will lead to the same results. The last equation on this slide is the estimating equation for the IRLS algorithm applied to logistic regression. To summarize, we have looked at more detail at logistic regression models in this module. To begin with, we considered the case of a single predictor and saw that the coefficients estimated by logistic regression have an easy interpretation in terms of baseline odds and odds ratios. This is one of the reasons why the logistic regression model is so popular in applications. We have next written out the likelihood, derived the score equation, the information matrix, and also the exact steps for the IRLS algorithm for estimating the maximum likelihood estimators for logistic regression. We have also defined the deviance and seen that while it performs satisfactorily for the case of grouped data, in case of ungrouped data, there is a problem which is well known in the literature as the problem of sparseness.